Io urlo tanto. Okay, I speak louder, so probably I don't need the microphone. So, my talk today, I want to give an overview on what is damage mechanics and how damage mechanics developed in the last 60 years, starting from the seminal work of Kashanov, that is commonly recognized as one of the fathers of damage mechanics. Damage mechanics is today an independent branch into the continuum mechanics, and everything started in 1958 in Russia. Kashanov firstly used the concept of damage as something that degrades the material properties, and finally will result in final fracture. I will recall this kind of concept later in my presentation in order to give, after these 60 years, what are the seminal concepts that has been developed and that are today commonly accepted and are part of the common knowledge into the mechanics of materials and in predicting failure in materials. Another seminal work was done by Rabotnov in 68, almost 10 years later, and going through the decades, a very important year is 1977, in which Gerson proposes, during his, as a result of his PhD thesis, a continuum theory of ductile rupture by void growth. He first introduced the idea that a material that is pressure insensitive can become pressure sensitive as soon as damage develops in forms of microvoids. Same year, the first concept and definition of continuum damage mechanics was introduced by Jensen and Hout, and also in the same year, Lemaitre and Dufay published the first paper on continuum damage mechanics, devoted to describe ductile damage mechanisms in metals and alloy. Later, starting from this year, a number of papers will be published, and a lot of work will be developed mainly in France and in Europe, and just later in United States. Lemaitre and Chabosh introduced in '78 the state principle for irreversible thermodynamics, which is the part of the work that I will address more in my presentation. Chabosh already in '81 proposed the use of continuum damage mechanics for ductile crack initiation in metals, and gave some guidelines on how to use this concept. And probably the most seminal paper is the one of Jean Lemaitre in 1984, where the first continuum theory for damage into the thermodynamic framework of irreversible process was published. In the subsequent decades, a very important work was done in Los Alamos communities by Curran, Seaman, and Shockey. This community is highly focused in the high strain rate behavior of material, so they were looking for description of the material and failure of material under very severe condition. And I will spend some words also in this area, which is part of the area that I'm working in, with my co-workers. Already in '89, we see the first review of review papers on damage mechanics. It means that damage mechanics was already in '89 a consolidated knowledge and had a community that was working full-time in this area. Later, starting from '89, most of the work in continuum damage mechanics was dedicated to trying to correlate experiments with theory, because up to '89, most of the work was basically a theoretical work. No connection with the reality, no connection with experiments, and this can have, had some drawbacks that I will discuss immediately after this. In 1997, I published my first paper in damage mechanics, and I have to tell that my work in damage mechanics comes basically because I was trained in a community in the University of Rome La Sapienza that comes from the that had the they were basically modelers, but modelers that thought at that time that a model has to be theoretically sound, not necessarily supported by experiments. So it was a turning point at that time. And this is, I would say, probably in 1995, we will see a shift from a different way to do research in mechanical area, in which everything was theoretically equation made by hands, solved by hands. The beauty of the model was the consistency of the formulation, the possibility to find the closed form solution. Experiments was seen as a sort of something not necessary to support the theory. And this is, for instance, if you go now back to the paper of Kachanov, it is today one of the most cited paper into the in damage mechanics, and you read it today for creep, has nothing to do with the physical creep process going into the material. So it's completely useless paper, but it's beautiful from the theoretical point of view. You come up with the sorts, you start from some first principle concept, derive some evolution laws. The fact that it has nothing to do with reality, this is not important. No experiment, no experimental data point in any of this paper up to the beginning of the 90s. So since then, this was also the year that I started working in the United States, and I had a different kind of approach, more practical, more in which you have to show that what you are developing has a practical applicability. So you have to provide physical evidence of the validity of your modeling approach. So we spend a lot of time in trying to provide experimental evidence to support model validity and to validate models. What is important is that in 2005, for the first time, continued damage mechanics appears in a handbook, and I think this is a very turning point. In 2013, the use of damage mechanics is allowed for the first time in design codes, such as the DMV. The DMV F101 is the design codes and prescription for pipelines. So for the first time, these new concepts are are allowed into the design of real components. And during these years, I can tell now that probably besides of a huge number of papers published in the literature, there are very few concepts that I call seminal concepts in damage mechanics that has been developed, and the value of these continued damage mechanics stems from the concept that I'm summarizing in the next few slides. The first is the concept of damage. The concept of damage in damage mechanics is different from the fracture mechanics community. The idea is that the classical crack initiation for fracture mechanics people is probably something in the range between 0.01 and 0.1 millimeter as initial crack or a physical crack, short cracks. In damage mechanics, there is a more distinguished length scale in which there is one word before the initiation of a macroscopic crack that is assumed in the range of 1 millimeter, and below this length, this is the range where continued damage mechanics works. As soon as you have a nucleation of the macroscopic cracks, this becomes the matter for fracture mechanics concept. The other idea is the fact that exists a critical state, and this final state corresponds to the macroscopic crack initiation. So we define in damage mechanics what is the end of some degrading process into the material that will turn out in a formation of macroscopic cracks, and the continued damage mechanics is dealing with what everything happened before. The other seminal concept, the second seminal concept in damage mechanics is the definition of damage. Before a final fracture, material undergoes a irreversible process that degrades or reduces the material properties and reduces the load carrying capabilities. If we assume that the damage is isotropic into a reference volume element, we will have that something develop, and we have a variable which is defined that has the ratio between the the damage area over the the nominal resisting area. And in the way how we define the damage in this way give us the possibility to deal with a material or theoretical or virtual material in which we define not the kinetics of the evolution of each damage, single isolated damage mechanism, but we capture damage in terms of the effect that that damage state has on the material properties. This is a really turning point because we detach from the physical description of the damage ongoing into the material, and we describe that damage state that can be complex as much as we want, has the sum of the effect that reduce the material load carrying capabilities. Another seminal concept in damage mechanics is the concept of the effective stress. So the effective stress is a concept that is derived from this approach, in which we say that if we have some damage, we can deal with a material, this is the virgin material, where we have no damage. If there is the damage, we have a distributed damage under stress sigma. We will have, or under a force F, we will have the stress is sigma times dA, where dA is the effective net resisting area. But we can deal, instead of dealing with this problem that is very complex, so we can deal with this problem, which we have a virtual material that has no damage, but has some degraded properties. This is a turning point, and in this equivalent material, the stress is no longer sigma, but is a higher stress, which account of not only of the reduction of the area, but also the concentration of stresses. So, in doing this, we have the possibility to get rid of the peculiarity of each damage form, shape, evolution into the material, but just capture outside the boundary of our body what is the detrimental effect. This gives us also the possibility to develop a constitutive theory, which is derived into the framework of thermodynamic of irreversible process using internal variables. I summarize the three important steps that are necessary to develop a constitutive model in damage mechanics. The definition of the state variables, which are defined in the observable or not observable or hidden variables. The observable variables are those that we can measure experimentally. The hidden just come from the model, so cannot be measured directly, but can be derived. We have to define the state potential, from which we can derive the state laws by the derivative. And finally, we have to define the damage dissipation potential for the evolution of the state variables, which are associated with the dissipative mechanisms. This is just three basic rules and three basic steps that can be used to develop a consistent thermodynamic model. In continued damage mechanics, by the use of the effective stress, we can simply assume that the constitutive equations for a damaged material is the same set of equations for a virgin material that come from continuum mechanics, just simply replacing the stress with the effective stress. So the system holds, but we have to introduce now an additional variable, state variable, which is the damage, for which we need a damage evolution law. And the damage evolution law can be derived providing the damage dissipation potential. The damage dissipation potential has to be to verify some principles. So, but at the very end, the important part is that, and this is one of the beautiful seminal concepts that derived in this framework, is the fact that for each variable there is an associated variable. Stress is associated to strain. Damage is associated to the variable y. The variable y has a physical meaning, because y is the strain energy release rate, which is not the Griffith criterion, but is the strain energy release rate that is released when the damage state, which is distributed into a reference volume, release the strain energy. So there is an equivalence also with fracture mechanics, because this is the same concept that Griffith formulated for a crack, for a propagating crack, but here we don't have a crack. We have a smeared crack into the volume, and this quantity can be physically measured. Another beautiful result is the fact that the effect of stress axiality on ductility can be theoretically derived without the need of additional hypotheses. Just partitioning the strain energy, strain energy into the volumetric and deviatoric part, and we can come up to this relationship in which y, that is the associated variable to damage, is a function of RV, where RV is a function of stress axiality. This gives you directly, without the need of additional hypothesis, the fact that the more triaxially the state stress, the lower has to be the ductility the material would exhibit. This is a fundamental concept that was initially demonstrated experimentally in the 60s by McClintock and Rice and Tracy, but in this framework, it just came up as a result of the formulation. We don't need any additional hypothesis. Then the game goes in the choice of the damage dissipation potential. In the literature, a number of authors provided possible expression for the damage potential. The damage, if you find an expression for your damage potential, then from this one you come up with the damage evolution law. So different damage evolution laws can be formulated. Some of them are very rough in describing the damage evolution in material, and again are not supported by experiments. I tried to, at that time, to find a damage dissipation potential that could account from the plastic strain history and capable to describe different damage evolution in different classes of material, to be as most general as possible. Another very important and seminal concept is the fact that if we have the effect of stress axiality embedded into our formulation, we can predict the so-called failure locus without the need of additional hypothesis. The failure locus is the correlation, is the place on a plot where we have the strain to failure as a function of stress axiality, and this place is theoretically predicted and can be in such a way verified by experiments. In particularly, there are different solutions in the literature, and of course you can validate this comparing with experiments that are usually provided with the tension tests on round notch bars, and I think that this is one of the key points in the very big value into the offered by damage mechanics. Of course, there are a number of issues still under discussion. I will quickly try to go through three different aspects that needs to be discussed, because today we are in a position where we want to transfer all this experience to the industry level in order to use this concept to predict resistance of real components in service. There are three aspects. The first one is that we know everything, as a scientist and as an engineer, we know what we can measure. If you cannot measure the quantity that we want to know, we don't have any clue or any information or any possibility to know what's going on into that phenomenon. So one of the requirements is, can we measure damage? The second is, I will discuss briefly on the issue of damage softening that for more than 1 decade took the attention of the research community. And finally, the transferability from sample to full-scale components and to different loading conditions. Very briefly, in the literature, Lemaitre proposes several methods for measuring damage experimentally. the most commonly, the most, I'll say, accepted method is the stiffness loss. You perform traction, loading, unloading, and you should see variation of the elastic modulus, and this is a proof of damage ongoing. The problem is that, unfortunately, this approach is incorrect, and we demonstrate this. The problem with the damage is that there are so many different physical damage mechanisms going into the material. If we look at the brittle fracture, ductile rupture, high cycle fatigue, there are some common features, but there are a lot of mechanisms ongoing. All of these mechanisms are deeply embedded into the microstructure. That means that if we look from the computational point of view, a reference volume element, which is the minimum quantity that provides you the homogenized properties of the material, there is a proof that you need just 200 grains for metals, in which beyond that volume you can no longer discriminate the effect of the orientation of the grains. So it means that a volume 5 times the average grain size by 5 times returns you the homogenized properties. Damage is a much smaller scale than this volume. So if we cannot capture the grain size effect on the overall scale, if you are sampling material volume larger than this one, how we can sample the damage effects? So the problem with damage is the fact that at the very end, I think I'm running out of time, so I need to skip some of this. The problem is that it not depends on the way you define damage. It can be defined in terms of porosity, it can be defined as a stiffness loss, but there are very low possibility to measure damage effects at the continuum scale. So, on the contrary, we can measure in a very accurate way the moment or the strain at which damage would start and the moment or the strain at which damage will end in times it becomes critical. And these are two critical points, two critical information important to identify the damage model parameters for a given materials. A very seminal work was done by Seaman Shockey that provide evidence that voids or particle becomes voids as a function of strain, and they were the first to use a sort of joined methodology using finite element simulation together with experiments. Damage softening. The damage softening is a big issue. There are thousands of papers assessing the fact that as soon as you have damage, the material softens, and the fact that it softens, then localizes, and that this opens a lot of issue from the numerical implementation because all the simulation, all the results becomes mesh dependent. The problem is damage softening real? I strongly believe that damage softening is not real. There is a big misunderstanding in the continuum damage mechanics history. This is a paper taken by Dufay and the French school. They were let's say identifying the initiation of damage as soon as the response of a tensile sample starts to go down, but in this way they were completely neglecting the fact that this was just a geometry response. So this is necking. It's a plastic strain development for ductile material. It has nothing to do with damage. And the fact that other people later, also in the French school, they said, okay, now this is not the initiation of damage, but damage initiation in a tensile test when we start to see this changing in slope. We proved that this part of the curve is just an artifact from the test that comes from the stiffness of your machine, and already here, as soon as you stop the test at this point, you cut the sample and you open up the minimum section, you find out there is already a macroscopic crack. So it means that once again, softening cannot be measured at the macroscopic scale, as the damage effects cannot be measured at the macroscopic scale. And so we can get rid of the softening. If you can get rid of the softening, your life is much easier because your computational analysis becomes no longer mesh independent. So the method is robust, and then you can use it in the practical application. Another issue was to provide physical evidence of the fact that if you calculate the damage distribution in your sample, then you have to have evidence that in the physical evidence of the damage distribution correspond to what you're expecting into the samples. In the past we made, this was a true comparison in which we simulate damage evolution in the uniaxial bar, and this was our gradient along the axis, and these were the porosity measure that were provided by people in Los Alamos, and if we normalize porosity with the critical porosity, we normalize the damage with the critical damage, so we have the same normalized graph, and so we can compare just the distribution. If you use softening, then you will have much more localized damage, which is not consistent with the experiments. Transferability. The transferability has to be done, has to be proved with respect to the stress, to the complex stress state. So you go from the uniaxial stress state to the multi-axial stress state, but also to different loading conditions. Just to go very quickly on this, in the past we spent a lot of time in order to demonstrate the transferability. We identify tests under uniaxial stress condition, then we transfer that on a multi-axial set of stress for notches, and this is provide the basic for the identification of the damage model parameters, and finally we predict without no need to further adjustment of the material model parameters, for instance the crack resistance and constraint effect in crack resistance curve. Another possibility is transferability when you want to describe a failure process in which two mechanisms goes at the same time. This is the case, for instance, for the ductile to brittle transition using the Sharpie notch, in which you have brittle fracture and ductile fracture competing. And again, if you use this damage mechanics concept together with, for instance, a probabilistic model as the modified Bellarmine model, is it possible to predict, without the need of experiments, just provide the material model parameters to predict the lower bound and the scatter band into the Sharpie curve, Sharpie energy curve. Just recently, we convinced an engineering company. This company was Saipem. Just recently, in the last, it was the last 5 years effort, that this methodology now is mature to predict the real life component, the real structural integrity of components. So we try to use this approach to predict to perform strain-based ECA, engineering criticality assessment, for welded cracks in pipes, and we provide them an approach, a practical approach. This approach relies on the fact that you have to identify firstly the flow curves of your material, and this is not tricky because this is dedicated to computational simulation. So we provide a procedure how to do this for the parent and weld materials. They identify the damage model parameters, performing very simple tests at the industrial level that has to be traction tests on round notch bars, and identified by retrofitting these failure data with finite element to generate the damage model parameters, validate these model parameters in predicting the fracture resistance in laboratory samples, and then use the model to predict fracture resistance in real life, in full-scale tests. I will quickly go to the final results. Okay, this is the validation for SEN-B, SEN-T, and CT. Again, when we identify the damage model, we don't change anything more. We don't have to go back and forth by new experiments to adjust the damage model parameters. This provides the basis for transferability. You can predict the crack resistance curve. And when we move to a full-scale test, as in this case, this was a full-scale plant in Germany that was monitored, and we were able. We were able to predict the overall response, the time from crack initiation, the extension of the ductile crack growth, and all the features that the pipe was showing in a full-scale test. The final point is that if the mechanism is the same, the model has to work in different scenarios, in different conditions. Working with people in Los Alamos, I was challenged since the '96 by Rusty Gray. He always was challenging us. They say, can you predict this? Can you predict this experiment? Can you predict failure in these experiments? And one key point is predicting spall fracture in the impact. In the spall, you have a disk impacting another disk. This is the target, a thicker disk. Because of the high velocity impact, the shock wave generated into the material goes as a compressive wave, is reflected as a tensile wave, then builds up with the release wave, and then you have a spall. You have a fracture occurring here. During this test, you can measure using laser interferometry the displacement of the free surface, have this trace, and the question is that as soon as you have fracture, you have some release waves coming into the problem. And this is very interesting test case, because here you have strain history, pressure wave going back and forth into the material. We know exactly the time where damage develops. Triaxiality is huge, because triaxiality in this case can go up to more than 20, which is something that you can never reach in geometry. And this is a very challenging task. Another task that we were very successful in predicting is the impact of a cylinder versus an anvil, which is called Taylor impact test, or rod-on-rod test, where you have a cylinder impacting another cylinder. For the same material, for the equivalent material, for equivalent velocity, if you do this test, you will never get, for a ductile material, you will never get damage. But you get damage in this case. So, a model has to discriminate the two tests. We demonstrated that our modeling of continuum damage mechanics was capable to separate the two effects. To predict that in the second case, in the rod-on-rod, the rod-on-rod is the one on top in that video, in which you shoot a cylinder against another still standing cylinder. In this case, you generate a lot of damage, and the answer is that if you look at the problem in terms of stress axiality, this is the stress axiality evolution in time, and therefore in strain, for the Taylor impact. For the equivalent condition, the stress axiality for the rod-on-rod is completely different stress path. So, damage can occur into the rod-on-rod, while it cannot occur in the Taylor test. And we provided the rationale, and also the fact that the model was capable to predict this behavior, while other kind of modeling specific developed for high velocity impact failing discriminated this behavior. What next? Where is going the research right now? The research in continuum damage mechanics is now moving to the shear controlled fracture. There was a lot of attention in the last 10 years on the possible role of shear in terms of described by the load angle parameter. Everything relies on this plot provided by Bao and Vitsbicki, in which there is a cusp in fracture strain versus stress axiality, because the uniaxial strain to failure is here, this is torsion, and this is the negative stress axiality range. There is a lot of effort in trying to predict the material behavior there. There you need a different kind of model formulation. For instance, the formulation I just recall doesn't account for J3, which is the third invariant of the deviatoric stress. Actually, there are evidence that this behavior can be observed in different materials. This is for Weldox, and a number of fancy samples has been proposed to test material in this condition, and we just recently extended the original damage formulation that I proposed in 1997 in order to account for the shear controlled fracture. We were able, and we succeeded with a very simple way, modify the damage dissipation potential, obtain damage rate equation which you have a stress axiality controlled plus load controlled terms, and you can predict failure in or the cusp in the failure locus plot. But the question is still today, with this method, we were able to predict, for instance, in shear in self-piercing riveting process, this kind of failure, which cannot be predicted without other kind of more traditional damage model, in which you have a shear fracture occurring into both material. This one is more brittle than the lower sheet. So there are some cases in which you can you will need for this additional damage modeling for shear. But we are still discussing about the possibility that this is this real? This is also an artifact. Just recently, Ravichandran revised the experiments of Bauer-Wiersbicki, and he proposed a much more detailed method how to measure strain at failure using grain deformation in the fracture surface, and he found that the failure locus is probably here, while others measured this. So there is a lot of discussion ongoing on what is the real material behavior under shear. But this is the part of the work that probably need to be investigated more from the experimental point of view, in a very controlled way, in order to provide reliable data that can be used then for to support modeling. A very interesting and conclusive results is provided by David Rittel in Tachyon in Israel. He developed a shear disk that overcome much more of the issues of the samples that Bauer-Wiersbicki used in the past, and he found another very different behavior. For instance, this is the failure plot into the positive stress axiality regime. Then you have a drop, and then you have a straight line in the negative stress axiality regime. These are much more reliable results. So if this is the case, if this is the real case, then we need to revise our model in order to predict this behavior in this regime. So sorry for being too long in my presentation, and I will be very happy to reply to your question. Thank you very much.